Hello, everyone. My name is Yafeng Yin. I'm a professor and interim chair of the Department of Civil and Environmental Engineering, University of Michigan. So welcome to the University of Michigan Building the Future Distinguished Lecture Series. In 2019, our department finished a 2-year strategic planning exercise through which we identify 5 strategic directions. They are enhancing human habitat experience, adaptation, automation, smart infrastructure finance, and shaping resource flow, which is today's topic. This direction explores the analysis and the control of the resource flow within our habitat to minimize their negative impact on the environment and the public health while achieving equitable resource management. So this is a very exciting focus for our department and also the profession as a whole. Our strategic vision reaffirms our value proposition to our communities and reinforce our commitment as an engineer working in service to society. To highlight our vision and to formulate a work plan, we launched this Building the Future Distinguished Lecture Series, which provide a forum to discuss each strategic directions. It's aimed to build a broad community network that include industry professionals, researchers, educators, and students. Through presentation from leading expert and panel discussion, this series provides new insight and explore a range of perspective on these 5 strategic directions. So we have had a lot of support to make this vision and today's webinar come together. We would like to thank our co-sponsor for today's event, National Alliance for Water Innovation and AECOM. I would like to thank the Strategic Implementation Committee led by Professor Sanyong Lee. I also thank Professor Lud Raskin, who's a professor here at the University of Michigan. Professor Raskin has agreed to serve as a moderator for today's presentation and panel discussion. I also would like to thank Joyce Kennedy, Michelle Santayam, and Reggie Varghese for providing technical and marketing support to today's webinar. A few more words on accessibility for the webinar. We want to make our event accessible to all participants. So this webinar will have a live automated caption. A transcript will be available. To choose a viewing options, click live transcript on the control bar at the bottom of your screen, where you can show or hide the subtitle or view the full transcript. I've now turned the session over to Professor Raskin.
Thank you very much, Yafeng, and welcome everybody. This is a really exciting event that we're all looking forward to. We will be emphasizing, as Yafeng mentioned, the strategic theme of shaping resource flow. And we want to show you a little bit more details of what we have in mind. So we would like to play a short video to introduce you to our theme and how we think about it. Yes, I was just going to say we can't hear the sound, so we should start over.
We would release it back out to the environment. We started to realize that a lot of those wastes that we would release have valuable resources in them. Civil engineers and environmental engineers were designing a lot of those flows. And so I think we have a big role to play in how we might continue to shift the mindset and think about, the future of what those flows might look like. One of the things I think we're doing that's really special is separating our wastewater right at the source, right at the toilet. And the reason that we're doing that is we can pull the nitrogen and the phosphorus out much easier before it's diluted in the wastewater, and then convert that nitrogen and phosphorus into really valuable fertilizer products. Researchers in CEE are building RECO blocks. These are blocks built out of materials from carbon that's been sequestered that are used to build structures. And then when the structures are done, rather than landfilling the material when we tear it down, we take those blocks and we use it in new buildings, shaping the flows of these resources rather than the linear flow, or making this a cyclical flow. In 50 years, if we're successful, this is just going to be in every activity we do as a civil and environmental engineer, how we're getting our resources, what we're doing with the resources and where they go when we're done with them is going to be ingrained in our work.
All right. We are going to get started here in a few minutes. I would like to just start with the introductions and remind all of the attendees that you can all put questions through the question and answer function or using the chat function on Zoom. So you can do that. You can start doing that during the lecture and continue during the panel discussion. And we will try to get to as many questions as we can. I'd like to introduce our special speaker and panelists. We are indeed very fortunate to have Dr. Amy Childress, Professor of Civil and Environmental Engineering at University of Southern California, here with us today, and she will speak to us on reclaiming wastewater with increasing salinity for potable water reuse. Then the presentation by Dr. Childress will be followed by a panel discussion with our distinguished panelists, Dr. Megan Mauder and Dr. Beverly Stinson. Dr. Mauder is an associate professor of civil and environmental engineering at Stanford University, and she's also the research director of the National Alliance for Water Innovation. And Dr. Beverly Stinson is the executive vice president and global water business line leader at AECOM. So I don't want to take any more time, so I'm going to turn over the floor to Dr. Childress to speak to us about our team and give her presentation.
Super, thank you, Lute. It's great to be here. I'm going to go ahead and share my screen and get started. Good. And just so the audience knows, before I start the presentation, I was asked to address a couple of overriding concepts of this seminar series. And the first one is how our society is moving from a use and discard mindset to a use and reuse mentality. And so this pertains to the circular economy that's become a hot topic. Water reuse, though, is not a new topic. We've actually been doing it in the LA area since the 60s and other places as well. But it's now a national discussion, and that's in part due to EPA's release of their water reuse action plan. Sorry. And I have a quote here from Megan Mauder, one of the panelists, that our linear water economy must evolve into a resilient circular water economy, where water is continuously reused and contaminants become the feedstocks for other economically valuable processes. So the contaminants we're going to talk about today are salt or salinity. And a key thing I want to point out is that we're not there with circularity of the salt economy. And a lot of that's because the business case for taking out salt and reusing it is often not there for something like sodium chloride from seawater. Maybe for certain ions, we're getting closer, like lithium and other high value constituents. But both of these are complicated by climate change impacts. There's less water availability in some regions, so this limits the water reuse or the wastewater reuse that can be done. And also the other side of that we don't talk about as much is increasing salinities in our water and wastewater. I'll be talking about that. The other kind of overriding theme to this circular economy is a one water mindset. And a quote from one of the other panelists, Beverly Stinson, is, one water is the awareness and acceptance of the reality that a water molecule doesn't change throughout its cycle. I also like to think of it as considering a water's quality, not its history. And we will be looking at blending two different feed streams into one, often two streams that have different salinities. And you might say, blending streams with different salinities, you're going to generate entropy and raise the thermodynamic least work to desalinate the water. How can that be good? But we hope to show there may be capital and operating savings and system advantages. And when I say system, I don't mean a facility, a single facility, but I mean our whole system of water use and reuse. And you might ask, wouldn't we be contaminating the streams by blending, or contaminating one stream by blending them? But we might suggest we're diluting the other stream with the blending process. Another concept, can one facility's trash or high salinity brine stream be another facility's treasure or water supply? In our study, we're going to look at the treatment of brackish water, reverse osmosis brines at potable reuse facilities. I had a discussion recently with Nikolai Buchkov, a practitioner, and I learned that in Israel, at one location in Israel, they're treating a brackish water RO brine at a seawater RO facility. So there's lots of facilities mentioned there, but the key thing is these facilities are beginning to interact. So the next question, how researchers can, or the next thought to expand on, how researchers can better engage with the broad community of practitioners. At USC, we're in the process of forming a water reuse and resource recovery center with a very specific goal of engaging and partnering with consultants and industrial partners. We have some good ideas. I'm not going to share them today, but I'll go on. A diverse team is needed to transition from problem solving at a local or regional level to translating solutions to other regions of the country or other parts of the world. So one goal of our work is to contextualize and create a framework around blending that has been done. So I would say in this case, we're the academics following what the practitioners have done. But we might ask, can the blending scenario that I mentioned in Israel be used to address similar challenges in Florida, Texas, or California, or elsewhere? But another goal of our work is not just to follow what has been done, but also to hopefully propose some new scenarios and ways of integrating desalination with potable reuse. And that's the building the future part. All right. So with that, I will get started on the actual lecture seminar. All right, so I'm going to start just by talking about a couple of California water supply portfolios. The first one I'm going to show is a more recent one from San Diego. This is a 2045 water supply portfolio. You can see they rely heavily on conservation measures, both domestic and industrial conservation. It's not really a supply, but it takes away from the supply that's needed. And then some reliance on the local surface water and groundwater sources, non-potable reuse, but what we're interested in is the potable reuse and also desalinated seawater. And a lot of facilities, especially in Southern California, are trying to wean off of this imported water supply, either from Northern California or the Colorado River. We can look at another water supply portfolio. This is an older one. The reason I bring it to your attention is because this is West Basin Municipal Water District. And for a couple of decades, they've been considering doing a seawater desalination project. And just in December, they voted to terminate going forward with that. So they are hoping to rely on reuse and imported water and some local groundwater as well. So there's been kind of a long-standing water reuse, seawater desalination. Which one will be the water supply of the future? And there's, of course, technology considerations. There's public opinion that has political implications. And this is important because the water board or the water agencies are overseen by boards of directors, and these are elected officials. So public opinion counts. There's also significant regulatory hurdles to both water reuse and desalination. In coastal regions, you might expect seawater desalination would win out, but if you also consider that the highest populations are along the coast, you have lots of wastewater available, and there's also a desire to stop discharging so much of our treated wastewater to the ocean. So there's still a competition there. The general consensus has been, of course, and as you saw in the portfolios, to do both of these. But I would say to do both in parallel. And what we are proposing is to see if there's maybe a way to do them both together. So I'm going to turn those portfolios into some blocks. We still have imported water and surface and groundwater, but we're bringing in potable reuse and seawater desal. So you might say, hey, why is seawater desal at the base? We know it's the most expensive water supply option. We think it is. We're still comparing to direct potable reuse, but in general, it's the more expensive water supply option. Do we want it in the base? But water agencies have to put it in the base to justify building these expensive facilities. We don't want facilities that can become stranded assets. So we say desal will be used as part of that base load. We will always use it. We won't mothball it. So I have to do a quick review of reverse osmosis before I go forward. I'll keep it quick. But in reverse osmosis, you have a pressurized feed stream. So this is water and some constituents that we're trying to remove, entering a membrane module. The permeate is what passes through. It should be relatively clean. And the concentrate or brine stream is what's rejected by the membrane. We have flow rates, pressures, and concentrations for each. Typically with reverse osmosis, people are interested in the rejection. How much of the constituents in the feed are rejected. And if you're looking at PFAS removal or something like that, rejection is important. I'll talk a little bit about recovery today, and that's how much permeate we take from the feed that's entered, how much product water we recover from the system. And for seawater, that amounts usually like 50% for when we're taking treated wastewater, sending it through a potable reuse facility. We are looking at RO that more often has more like 80% recovery. Okay, so here's our coastal water system that's fed in part by a seawater desalination facility. Seawater comes in, desalinated seawater makes up part of the water supply, and a high salinity brine stream is discharged back to the ocean. We have our other sources, and on the other side, we have the wastewater coming out to a wastewater treatment facility. Traditionally, in the past, we've sent all of the treated wastewater to the ocean. Now we might pull off a portion and treat it to maybe through filtration or something for non-potable reuse. And we might take another portion and either treat it on site if there's enough footprint available, or send it to a neighboring advanced water purification facility where we're treating it for potable reuse. So here I'm showing wastewater RO. It's not the best acronym because it's really treated wastewater RO, but just to differentiate it from the seawater RO over here. If we focus on just these two streams that are discharged to the ocean, right now we co-discharge. We use the treated wastewater and mix it with the high salinity brine so that we can bring the salinity down to regulatory levels and discharge it into the ocean. We asked, can we achieve these brine discharge regulations somehow without wasting the water resource? Because that's a waste of the water resource in the treated wastewater. So study number one was two scenarios, a co-discharge scenario. That's what I just showed you. So we have the seawater coming in, the brine stream coming out that were blended with the treated wastewater. Just to give you a ballpark, seawater, we're approximating it at 35 grams per liter. And we're gonna set a typical standard, just something in the ballpark of 40 grams per liter. And you'll notice that we're using an energy recovery device. These devices are typically used in seawater RO facilities, and they transfer the energy that's left in that RO concentrate back to the feed stream. So they reduce the high pressure requirements that are needed on this side. We're going to compare that with what I'll call a potable reuse scenario. This does not exist now. It's a proposed future scenario where instead of doing brine blending, we're proposing feed blending. So we're bringing that treated wastewater in on the upstream side. We do account for some advanced processes that would be needed, and we're proposing then to blend that treated wastewater with our intake seawater. And we looked at blends from 0 to 100%. 0 would be just a full seawater RO facility. 100% would be just a wastewater reclamation facility. But really, we were interested in the blends in between those. And so the blend that I'm going to show you some results for was a 60% treated wastewater, 40% seawater blend. This is snapshot results for those two scenarios. Here we're looking at flow rates as for the two scenarios. So the brine blending scenario, 100% seawater, no wastewater in the influent, and the potable reuse scenario, which was 40% seawater, 60% wastewater in the influent. So the things that we can see immediately is in the potable reuse scenario, we need a lot less seawater. That means less seawater intake infrastructure. That's a big deal, cost-wise and for the environment. If we look at the gray bar, we see that with the potable reuse scenario, we're discharging less water. So that's less discharge to the ocean. And if we look at the yellow bar, which is net specific energy consumption, we see the potable reuse scenario has a reduced energy requirement. That's in large part due to the fact that because of the blending, we wouldn't need a second pass RO for boron removal. Normally for boron removal, we take the permeate from a first RO train and send that to a second RO train to get a high enough boron removal. But if we're blending these streams, we can get that savings, get a significant energy savings. So where this took us was we should move potable reuse into the base. There's so many reasons that potable reuse has benefits over seawater desal. So let's move that into the base. But if we go back and look at the treated wastewater flow rate as a function of the ratio, remember I said we went from 100 to 0. So this is 100% seawater. This is 100% wastewater. And we picked the 40/60 because it was where we no longer were doing discharge dilution. So that would be wasting that water resource just by blending it for discharge. So we wanted to operate outside of that, but still meet the discharge requirements. So we did it with influent dilution at 40/60. But if we step back and consider those benefits of doing potable reuse or using the treated wastewater, we might ask how much treated wastewater is available, and why not operate in a 20% seawater, 80% wastewater scenario. And it was at this time that we realized our paradigm was changing from wastewater augmented seawater desalination to more of a seawater augmented potable reuse. And I'm going to come back to that topic of seawater augmented potable reuse. But before I do, I just want to go back to our blocks. So if we can minimize the seawater desal, we can address some of the brine discharge concerns. We can reduce the seawater intake. We can reduce the energy consumption, some of the energy consumption. But we still have seawater desal down towards the base. So we're not addressing the demand risk. And that's if less expensive water supply options become available, then our demand for seawater desal would decrease. It's the concern to have a stranded asset, a mothballed seawater desalination facility. So before I address that, let me just go forward with our summary from study 1. I hope I showed there's multiple benefits of the potable reuse scenario. We still left this with how can we protect seawater desalination from demand risk? And is there enough wastewater available to meet potable reuse demand? are other sources available? So I'm going to touch on this one first, and then I'll come back at the very end and touch on this one. This leads us to study 2, where we step back, we're looking at potable reuse of reclaimed wastewater with increasing salinity. So now we're not looking at seawater RO, we're looking at a wastewater reclamation facility followed by an advanced water purification facility with an RO process. We have our wastewater influent coming in. The salinity has been increasing in wastewater. This is due to residential water treatment systems, industrial uses, water conservation, and our existing reverse osmosis has been accommodating that additional salinity. Not only that, seawater inflow and infiltration. So there can be leaky gates or corroded infrastructure that if you have a facility in a low-lying area, seawater can intrude and mix with that influent wastewater. So that also contributes to increasing salinity. And the key is that both of these are exacerbated by climate change, sea level rise, and more water conservation. So our first question was, can we use our existing RO systems to treat more salinity, maybe higher salinity waste streams that could provide additional supply? So the first thing we considered was that you may have a regional brine interceptor that collects and conveys brines from desalters or concentrated waste streams. Right now, those may be treated in a wastewater reclamation facility and discharged to the ocean. Could we instead treat those for reuse? So an example scenario of this is Orange County Water District's groundwater replenishment system. They're expanding from 100 to 130 MGD. Could a portion of flow in a regional brine interceptor give them additional effluent or additional influent that's needed? We also considered brackish water reverse osmosis brines. Could we put those in upstream of the wastewater reclamation facility or downstream of it? Now, this does happen in a few cases, but it is certainly not industry standard. Instead, in inland regions, some of these brackish water RO brines or not some, but they're typically discharged to disposal wells or evaporation ponds where we lose that water resource. So if we can recover these flows by blending and desalinating them, what would the energy implications be? So before I go to combining those two, I'll also say that both of these are often limited. The capacity of brackish water RO facilities is limited by the brine discharge regulations. So if we can find something better to do with that brine, we might have more capacity available at our brackish water RO facilities. But combining both of these into and refining our question, can these higher salinity streams be treated at no additional energy cost using devices or processes typically not implemented at advanced water purification facilities? The RO systems we considered, a 2-stage RO, and this is pretty standard for brackish water RO or wastewater RO, is treating the concentrate from the first stage and the second stage. And by doing this staging, we can decrease the irreversible work or the energy that's lost in the process. We also looked at using an energy recovery device. Now, you saw the energy recovery device earlier, but that was for seawater RO. ERDs are industry standard for seawater applications, but they're typically not used for wastewater or brackish water RO applications. So we looked at the possibility of using an energy recovery device. We also looked at using high recovery RO. I'm not going to include those results today just to keep it streamlined. This is the framework we put together. I'll point out a few key things. We have the wastewater coming in. We have seawater intruding in. We looked at 0, 2.55, 7.5, and 10%. And then we looked at the possibility of bringing in the higher salinity streams. So that would be 5.7, 7.5, 10.9, and 17.5 grams per liter. This combined stream went to an advanced water purification facility. We're trying to have water for potable reuse that meets certain salinity requirements. And we're also discharging a stream that also has regulatory requirements on it. So here are some of the results. You're looking at the specific energy consumption, the net specific energy consumption for the 5 seawater INI scenarios. So 0, 2.5, 5, up to 10% seawater INI. And we'll just take one of these example scenarios. The yellow represents we're bringing in the regional brine interceptor. The next bar up is a brine 1, brine 2, and brine 3. The black dots are the influent salinity. So we can see that we're going in the direction of influent salinity. If we compare the base case, so that's this first bar and the red line, we see that if we bring in brine 3 to this 0% seawater INI case, we have a 69% increase in energy required. Whereas if we look at the 10% case, so our background salinity has increased, we see that the percent increase for brine 3 is only 34%. And this is interesting because it means as our salinities come closer, the rate of increase of SEC net decreases. So in time, perhaps higher salinity streams won't seem so much higher. Now, these results, all you're doing, you're looking at this bar, it's the bar you just saw. So the left-hand bars are the bars we were just looking at. The right-hand bar next to them is if we are using an energy recovery device. So now we can look at the energy savings if we implement an energy recovery device. So that's the difference between the bars. And the thing to note is that in the lower background salinity case, we see that the second bar is above this base case, which means the ERD can only partially compensate for the additional energy required. But if we look at the higher background salinity case, where the second bar representing the ERD results is lower than this base case line, we can see that we can fully compensate just by implementing an ERD. We can fully compensate for the additional energy required. Of course, you have to weigh the capital cost and perhaps a slightly additional complexity of using an ERD, but we can fully compensate for the additional energy required. And I should note here that it's not just TDS or salinity and specific energy consumption that are important considerations with bringing in these brine streams. We also have scaling, and we did in the paper that I'll give you the link to at the end. We did look at scaling potential, and in some cases that may limit how much of a brine stream you can use. But from the perspective of treating that brine, there's significant benefit with blending it with the treated wastewater, because then you have less scaling potential than if you were just treating that brine stream alone. And interestingly, Tom Pankratz in his water desalination report at the end of March called out a facility, a brackish. So this is now brackish water RO facility in Florida that's implementing, this is a first time implementation of this ERD. And they're trying to accommodate future anticipated increases in salinity of 20% per year. And they project significant cost savings with using an ERD. And the reason this is important is just to show that accommodating these salinity increases is important. This is not an example of different facilities combining streams. But we were excited to see kind of similar results because brackish water RO facilities, like wastewater RO facilities, don't typically use energy recovery devices. And as promised, I'm returning to the future of seawater augmented potable reuse. And if we go back to our structure of a wastewater reclamation facility and an advanced water purification facility, we are also asking, could we augment that treated wastewater with seawater to meet potable reuse demand? And at face value, looking at this, you might say, what? That's crazy. Seawater, wastewater, salt, organics, you can't do it. But we would point out that really it's a transition from this incidental or unplanned or de facto seawater desalination to an intentional desalination of seawater. And maybe it would only be at 10% or some low level. All right. Oh, and the most important part is, in doing this, we can take that seawater desal block and move it up into more of a peaker position, because now we're not relying on new desal infrastructure that could become a stranded asset. Instead, we're using our existing infrastructure or modifying our existing infrastructure to do this as needed. So, summary and concluding thoughts. Frameworks were developed to evaluate current and future blending scenarios for saline and wastewaters. In the near term, minor to moderate retrofits of potable reuse facilities can allow treatment of these higher salinities without significant energy increase. But in the longer term, taking an integrated facility perspective can help address future energy and environmental concerns. And I want to acknowledge my co-authors, Xin Wei. This work started as part of her PhD, and the papers that, if you would like to read more, are here. And Bana Datta, who's working with me now at USC. I also want to acknowledge Kelly Sanders, Andrea Achille, and Zach Finger, who were co-authors on our first paper. Oh, additional acknowledgements real fast, the funding agencies, and of course our practitioners, in particular Bob Oland at Dudek. We wouldn't have put this together without them. All right, thank you.
Thank you so much, Amy. This was very impressive to put so much information in the short time that we gave you. I learned a lot, and this topic is really moved along very much since I've last seen you to present. So I have a few questions from the audience that we had submitted, and some of them you've already answered in your talk, but I think it may be worthwhile to still have you address some of them. And one is kind of a big picture thing. When people think about RO systems, we think about them as expensive. So do you think they will continue to be part of the portfolio for reuse? From your talk, it looks like you think so, but I would like to hear your perspective on that question.
That's a great question, because there's so much pushback on RO systems, and a lot of interest in developing non-RO systems for potable reuse. I think there's space for both. I don't think RO systems will be replaced, though, because of the salinity issue. Even in regions of the country where you wouldn't expect increasing salinity to be a concern, it is. So maybe until we get at the roots of that, I think RO has firm footing but of course not in all processes, but in many applications.
Okay, thank you. And I'd like to invite Dr. Mauter and Dr. Stinson also to come in and see if they have any comments on that from their perspective. I see you unmuted, Beverly, so go ahead and provide your thoughts.
I'm not particularly expert in that, but one thing I know recently, and I know that you didn't talk about this, Dr. Childers, but the closed circuit RO You didn't go into details on the results of that, but we're getting about 95% recovery with closed circuit RO, which I think is a big deal when you put all that infrastructure ahead of it. You've upgraded your wastewater treatment facility, you've increased and added all of the extra infrastructure for MFRO and so forth. And so to get all the way from 80 to 95 seems like a pretty good idea. What's your thoughts on that?
Well, closed circuit RO, if I'd have shown the graph, it does have more savings. So I think it's very important. It's being pilot tested at a lot of facilities. Also flow reversal. So RO using flow reversal is gaining a little traction, especially for those treating brackish groundwaters. So I think those two, and I know also there's a batch technology. So CCRO is semi-batch, but there's also a batch technology on the horizon. So I think it's exciting. I think all three of those will play a role as well.
Okay. Megan, do you have anything to add?
Sure. I'll just add in sort of a response to the broader question of where is reverse osmosis as a technology going. And I think, as Amy pointed out, we are using reverse osmosis to treat a wide variety of feed streams. That includes seawater, that includes brackish water, and that also includes municipal wastewater. I would say finally that we use RO quite a bit for kind of polishing applications. So from a technology basis, reverse osmosis is a phenomenal technology when you need ultra pure water on the back end. The question I think that researchers are tackling is, where do you really need membrane-based technologies, and where do the advantages of modularity and manufacturability trump some of the energy implications of using membrane-based technologies? And are there ever instances, especially in municipal wastewater reuse, that you can get away with not using a reverse osmosis membrane setup so that your overall energy it could be lower? That's not going to be the case in the examples that Amy showed, in which you're blending seawater in because you need to manage those salts. But there may be some applications where you have lower salinity streams and you're not anticipating salinity increases, where you can get away without removing the salt and simply drawing down that TDS through blending.
All right, thanks. Let's move on to another question from the audience that kind of relates to this last question that just showed up in the chat from Glenn. People are wondering about zero discharge salinity, salt recovery, and recovering resources from the brines. Can you talk to that, Amy, or panel members, Megan and Bev?
Yes. So zero liquid discharge means different things to different industries. For example, coastal wastewater treatment plants, it means approaching no discharge to the ocean, but that is not viable at this time. So then facilities are looking at this high recovery RO to discharge as little as possible. But if you look at power plants doing ZLD, typically it's a high recovery process, and then sending the brine to an on-site discharge well or evaporation pond. So it's a little bit cheater ZLD, but it's no liquid leaving the property. And yeah, that is the direction for sure. I don't know if the other panelists want to comment.
I think there's one facility that we were working at where we actually recovered some products and beneficially reused them. And that was to some degree in a range of different uses, but it was an aspirational project. And from a financial perspective, it was certainly interesting and it's viable, but cost effective, not quite there yet in the beneficial reuse. But I do think that's, with the way commodity prices are going, that whole economic analysis might have slightly changed by now. So I think it's definitely a desired direction, is beneficially recovering and reusing some of those products.
And I'll just sort of add in to say that there are some high publicity projects right now, NEOM in Saudi Arabia being sort of the primary one that is really trying to implement a future in which those salts might find economic value. I think that's a very difficult value proposition here and with today's technology, but you know, there may be a path forward. If you're going to pursue that, though, I think it's incredibly important, as Amy alluded to in the beginning of the talk, to really think about what the economic value of these products might be. That economic value is going to differ tremendously based on what your feed water is and based on what the water quality that you need from your product stream is. So I would just say that maybe more than anything from a research perspective, we need tools to help us understand the ability to recover different constituents and really good planning and design tools that also help us think about the vast array of different types of water quality and end uses for that water quality.
We have a related question in the chat from Dr. Chirang Dong. So he is wondering about the brine and treatment of brine. So that's a different topic that we haven't really talked about. But if we're now going to have these brines that are coming from seawater and treated wastewater RO facilities, will they still be treatable using biological processes? Because those characteristics are going to be quite different with perhaps higher nutrient levels, different salinities, and so on.
Yes, and so the quality of the brine stream is key to being able to discharge it. And so people are looking at processes to treat that brine stream before discharge, or going upstream and looking at how to improve the biological processes upstream so that there's less in the brine that has to be dealt with. But that's, I think, a wide open research area and exploration area right now.
Okay. So we have a few more technical questions, but I also would like to move to some of the slightly less technical questions to get your perspectives, especially the panelists' perspectives on this. So what are strategies in terms of going with this potable reuse to you know, our non-technical perception-based issues that we have to convince the public that this is a good direction to move towards? What are strategies that we can use for that? And some questions that came up in the chat while you were talking, Amy, related to this, I believe, in terms of the terminology that we use. So you use the term treated wastewater. You know, should we completely change to used water, for example, was one of the suggestions that came up in the chat.
Yes, I think that is a good idea. Yes. Yes.
So there,
yeah, Beverly or Megan wants to comment more. I agree. As we're reusing more of our wastewater, our terminology around it definitely needs to change.
And I suspect that was Dr. Dagger might have come up with that, because he's been involved in Singapore, where it is called used water, and I think that's a really good comment, actually, that we need to adjust our references, and I think there's other things as well, which I think Singapore has been a really interesting place to discuss how to encourage and to drive recycled water, new water, as it's referred to. And some of their lessons learned are most certainly around scientifically based arguments, I think, as well as the emotional arguments and the benefits. So separating, for instance, the chemical or the industrial streams from the domestic wastewater streams has been a helpful approach there. And that has meant that there are improvements in the base quality of water that's being recycled. and industrial water can be recycled for industrial use. And so that's been helpful. I think also discussing the use of those and blending of those beneficial reuses with a brackish water / the Keppel, the New Marine East Keppel desal facility we just completed, which deals with both brackish and true seawater, salt water, depending upon the season, and blending that. So there's a lot of strategies that I think we can look to Singapore to close that water cycle, and our terms of reference are indeed part of that. Yeah. So good science-based information to support social, the manner in which we address it socially.
Just adding on there again, I completely agree, Beverly, that thinking both about what are the feed waters coming into reuse facilities, and also what are the end uses for that reused water is really important. There may be instances in which we get great economies of scale from doing this all in the same place in a single facility. There may also be some real benefits to thinking about more small scale distributed systems where you can reuse that wastewater on site and vastly reduce your demands on the municipal infrastructure that is used to distribute drinking water. I mean, the reality is that like 20% to 25% of our water use is municipal water use, and of that, maybe 1 to 2% is actually consumed. And so we really need to start thinking about ways in which we can protect public health and really maximize the water quality that is consumed, but also diversify the set of waters that are used for these other end use applications.
So other than the terminology that we talked about and the science-based information sharing, any other strategies for the public? Or maybe we could talk about policy, like how could policy help promote moving towards the circular economy?
I do think in some places there are so many multiple benefits from recycling water, and I think about it's not a membrane-based system, but it's a carbon-based, BAC-GAC system that's being installed in some facilities. And the purpose there is not for direct potable reuse, but for groundwater replenishment and storage, and for later recovery and reuse, which is also, I think, a really important part of the overarching strategy, because we do need to, when we switch between supplies as they are available and store when possible and recover when those other sources are lacking. So the groundwater recharge and replenishment helps to prevent saltwater intrusion. It helps to prevent land subsidence. It provides that sort of banking of water. So I think all of those strategies, coupled with the work that Amy's talking about with optimizing the blending of salt water and seawater through membrane-based systems. I think when you put all the myriad of options together, the conglomerate of energy plus reliability and resiliency all have a factor on how you address these different water recovery options.
We are in a sort of a future in which focus on carbon intensity of our industrial and sort of broad infrastructure processes is going to be really, really important. And yet we're also talking about implementing a set of technologies that, quite frankly, is pretty energy intensive, and meeting higher water quality requirements often means adding in all those additional processes. So I think from a policy and regulatory perspective, there are two important things to keep in mind. One is that we really do need flexibility in meeting water quality requirements. I saw in the chat kind of a comment by Charlie saying that, yeah, in California, the de facto standard is to put an RO train in there. Well, is that necessary from a public health and public safety perspective, or are there other approaches that one might take if we're thinking about overall, managing this overall risk of climate risk and exposure risk, especially if the end use of that water isn't always drinking water. I think the second really important piece here is thinking about ways in which infrastructure systems can start to support one another. So we have an energy infrastructure system that is rapidly changing, and we have a water infrastructure system that is rapidly changing. And thinking about ways in which those two infrastructure systems can support one another, that they can co-develop, I think it needs to be a big focal point, both from a scholarly perspective and from a regulatory perspective.
Yeah, I just want to add here a point that Nancy Love just made in the context of this discussion with communication about these technologies, is the communication about risk. So we don't do particularly well with that. So she is suggesting that perhaps we need to spend more time on communicating science and engineering risk to the public and our audiences. So any comments on that?
I will just say that EPA right now is looking at cumulative risk assessment, or what they're calling cumulative impact assessment, where they're looking at how we can combine, or how we can look at combined risk from exposures to chemical and non-chemical contaminants. And I think a very important part of that is outreach and interface with the public, and how to, of course, mitigate the risks, but also communicate. So I think EPA is working in that direction, definitely.
I'll point to a large body of work that my colleagues here at Stanford and also at Berkeley did through ReNewIt on outreach and communication of potable and non-potable water reuse sources. I think one of the most important things is to be very direct about what our water sources are, being very proactive and engaging the community early on. And as Amy said, being very forthright about risks and also contextualizing risks. The EPA also did a lot of work, actually. There's a huge body of scholarship in the 70s and 80s that's interesting to dig into. I'm happy to share a lot of that work. I have some very old EPA manuals in my office about risk perception and risk communication, not usually specific to water reuse, but all of those same principles really apply to how we need to engage the public and how we need to communicate that risk long term. I also would say that I think, there in the water sector, there's this interesting phenomenon where we kind of like always need to demonstrate or pilot something on site. And there's, I'll point to a colleague, Zahi Kath, who was actually one of Amy's earliest students, but he has a direct potable reuse trailer that he's using both as an educational platform, but also to kind of go from literally municipal wastewater treatment facility to municipal wastewater treatment facility, demonstrating that it works, right? And I think that often like the proof is in the pudding for a lot of these operators. There's very little incentive for them to take new risks. They don't want their systems to be non-compliant or to fail. And so adoption of these technologies is actually by the operator is actually really hard. And these types of small scale movable pilots that can really help operators and the public both familiarize themselves with reuse as a concept and the technology as sort of a series of functional devices that can be really powerful from a demonstration perspective.